Good morning all of you. Welcome back to analysis of indeterminate structures. In previous sessions, we have solved simple continuous beams subjected to different kinds of loading. In today's session, let us consider a continuous beam subjected to 2-point loads along with a support settlements. Here, the support B and support C will have a settlements of 10 mm and 5 mm respectively. So let us see how to solve this kind of problems by using flexibility approach. So in previous problems, we have used conjugate beam approach to solve the problem. So here, since we have support settlements, we need to use unit load method to solve this particular problem. Clear? So as usual, the step remains the same except we use unit load approach to solve the problem. So here unit load approach is the basis for solving this particular problem. So let me call this as figure A, the given beam. We have step number 1 to find the degree of static indeterminacy. As you all know, degree of static indeterminacy gives me the order of matrix. Clear? So here as usual, count the number of unknowns. At A you have fixed, therefore I get 2 unknowns, plus 1 3, plus 1 4. Therefore 4 and available equilibrium conditions are 2. Therefore degree of static indeterminacy is 2. So I can say this particular beam is indeterminate to second degree. So here in previous problem we were selecting moments as redundants, and I have told you even you can select reactions as redundants, but whenever they give support settlements we should take reactions as redundants. Which reactions? I have 3 reactions. I get reaction at A, B and C. Now I should select the redundants at that particular points where they have given support settlements. Since support B and support C are getting settled, we have to take RB and RC as redundants. Clear? Therefore here the redundants will be reactions at the supports B and C, that is RB and RC, and along these redundants we should mark the coordinate direction. Clear? Therefore at RB I get coordinate number 1 and at RC I will get coordinate number 2. Now as usual, after finding the degree of static indeterminacy and marking the redundants, we should write the released structure. Clear? That is the determinate structure. So our released structure will be like this. So if you remove the restraints at B and C, this will be a cantilever beam which is having fixed end at A and free end at C along with the applied loading. At B and at C, I will remove the restraints, that is redundants RB and RC. So now span remains as it is. So this will be figure B, released determinant structure. So you need to remove the marked redundants, that is RB and RC. Next, I should mark the coordinate directions along the direction of redundants. So I have one redundant at B, therefore this will be my coordinate number 1, and second redundant at C, therefore this will be coordinate number 2. you can mark the coordinates in downward direction also. But remember this, whatever the direction you have taken, that particular direction will be treated as positive. Clear? So this is, I call this point as D and this point as E. Clear? As usual, this is A, D, B, E, and this is C. And you can call this particular diagram as coordinate direction. This figure C shows the coordinate directions. Clear? So this is the major change here. We need to mark the reactions where we are getting the settlement as redundants, and along those redundants you should mark the coordinate directions. And you have to remove these restraints. So that gives me the released structure. So this is step number 1. Clear? And here itself you will get to know the size of the matrix, that is order of matrix. Our matrix size will be 2 cross 2. And in step 2 we use unit load method to get displacement matrix and flexibility matrix. For that I should refer figure B, that is the release structure. Along with this figure B, I need to draw 2 more diagrams to apply the unit load along the marked coordinates. So here, to find delta or theta, we use the expression from unit load method called m into m dx divided by ei. Clear? Where capital M gives me the respective bending moment in a segment due to applied loading. That means I'll make use of figure B along with the applied loading to find M. Clear? So this small m gives me the respective bending moment in a segment due to unit load. And where we are going to apply the unit load? We apply the unit load along the respective coordinates. Therefore, here to find m I make use of the release structure, and to find this small m I need to draw 2 more diagrams, one for coordinate number 1 and the next one is for coordinate number 2. Clear? So let me draw those diagrams. Clear? So this is D and this is B and this is E and this is C. So here we are going to apply the unit load at coordinate number 1 and we remove all kind of loadings. That means here whenever we apply unit load, we need to remove the applied loads, that is 80 kilonewton and 40 kilonewton. And in the same manner you can take the second diagram mark all the points, and here we are going to apply the unit load at coordinate number 2. So as usual the span details remains as it is. So we can call this particular diagram as figure D, so which gives me the details of unit load applied at coordinate number 1, and this particular diagram as figure E and here I can get the details of unit load applied at coordinate number 2. Clear? And now we use figure B, figure D and figure E for further calculations. To apply the unit load method, let us make one standard table, so which consists of segment. In this particular table you can get the details of segments you have, then origin, limits, then EI, then I should give the information about moment because of the applied loading. Look at this expression here, capital M gives me the bending moment in the segments because of the applied loading. To get this capital M, I take the help of figure B. Now, since I have two unit loads, I'll write M1 and M2, small m1 and small m2. That means, so this gives me the bending moment because of the unit load applied at coordinate number 1, and this gives me the bending moment because of unit load applied at coordinate number 2. So, let us complete this table. How many segments you have? Just refer figure B, D and E. I have AD, DB, BE and EC. 4 segments. Make 4 columns. The segments are, since it's a cantilever beam, I'll go from the right hand side, that is free end. It is CE, EB, then BD, then DA. Clear? So these are the segments we have in a particular beam. Clear? Next, origin. So I can take the starting point as origin. Clear? For individual segments. Since in CE, C is the starting point, I'll keep C as origin. In EB, I keep E as origin. And in BD, I'll keep B as origin. Likewise, in DA, I'll keep D as origin. Clear? In this segment, I'll keep C as origin. For second segment, E is the origin. And for third segment, B is the origin, and for last segment, D is the origin. And you can take C as the common origin also. Clear? So it's left to you. Now, based on the origin taken, we should mark the limits. See, since we have taken C as origin, the limits will be 0 to 2. And here, since we have taken E as origin, the limits will be again 0 to 2. And if you take B as origin, again the segment span is 0 to 2 and last segment is also 0 to 2. Next, if you write down the EI details, clear? So look at the question. So they have given variation in EI, that is they have given for AB it is 2I and for BC it is I. Therefore, for first 2 segments, EI variation is 1 and for the last 2 segments, EI variation is 2. Write down that particular information. Clear? Next, we should fill up these details by taking moment about particular point. Clear? So just write, to take M, capital M, I use figure B, and for M1, figure D, and for M2, I'll make use of figure E. Clear? So let us take the sections in between the segments, and we need to take the moment about that particular points. Clear? So now refer figure B. So this is a structure. So here between first segment, that is between C and E, I take section XX. From origin, that is C, I'll mark it as small x. Now you need to take the moment about this point. We are considering right side of the section. Clear? So take moment about this point. So to take moment about this point, to the right side of our structure, are we finding any particular load? No. Therefore, moment about this particular point by considering C segment is 0. Likewise, you repeat for all other segments. Let me take the second segment, that is EB. In between EB, you just take the section XX. Now, you have taken E as origin. Therefore, from E to this particular point, I will mark the distance as x. Now you need to take the moment to this particular point. Clear? So now take moment by considering the right hand side of the portion. So it is 40 into x. Any other load to the right hand side of the section? No, we can find only the 40 into x, and this acts in downward direction. Therefore, the moment will be minus 40 into x. If you fill up this particular table properly, the next steps will be very simple. In further steps, we are going to apply simple mathematical operations. So now take section in segment BD. So since you have taken B as origin, mark x from B. So take moment about this particular point. Clear? So I have 40 till this point. 2 plus x, load into perpendicular distance. Again this acts in downward direction. Therefore, this will be minus 40 into x plus 2 or 2 plus x. Likewise, take the section in the last segment, and since D is origin, mark x from D and take moment about this point. Clear? So once you take moment about this point, you forget about this particular section. Clear? Now the new section is here between the span DA. Now take moment about this particular point. What do you get? It is 80 into x, then 40 into x plus 4. From E to D, I have 4 meters. From D to this particular point, I have x. Therefore, it is 40 into x plus 4, and because of 80, I'll get moment about this particular point as 80 into x. And all these forces creates downward moments. Therefore, you can write them in negative sense. It is minus 80x minus 40 into x plus 4. Clear? You can simplify the expression and write it. Clear? 80 into x, then 40 into x plus 4. If you simplify this particular expression and write minus 80x minus 40x, it will be minus 120x. Then minus 40 into plus 4, it is minus 160. Clear? So like this, by repeating the same procedure for figure D and E, we can fill the details required for M1 and M2. Clear? So now to get the details regarding M1, that is unit load applied at coordinate number 1, remove all the applied loads and apply only the unit load at coordinate number 1. As usual, take the segments. First, we take the section in segment CE and call this as x. Take moment about this point. To the right side of the section, are you find any load? No. Therefore, moment about this particular point is 0. Again, take the section in segment EB. Will you find, and this is X. Will you find any load which creates moment to the right side of the section? No. Therefore, again, moment about that particular point is also 0. Now, take the section in the third span, that is BD, and from B to this point, call this as X. Now, take moment about this particular point. We have unit load 1 kilonewton multiplied by the distance X, and this gives me the upward moment. Therefore, it is 1 into X. So, I will get plus X here. Like that, for the last span, that is for the last segment, that is AD, I have unit load 1 kilonewton into perpendicular distance 2 plus X or X plus 2. Therefore, I will get 1 into X plus 2. Simply I can write it as X plus 2. And again, this gives me the upward moment. Therefore, I will write it in positive sense. Like that, we will repeat the same procedure to get the details regarding M2. Clear? So, take section between EC. So, call this as small x. 1 into X, it is X, and here from E, I will mark the value as X. 1 into X plus 2. Therefore, it will become X plus 2. Now, here it is 1 into 2 plus 2 is 4, and this is X. It is X plus 4. And in the last segment, if you take the section and mark it as X, it is 1 into 2 plus 2 4 plus 2 6, and this is X. It is X plus 6. And if you have DSI as 3, clear, then we will get one more moment M3 for the coordinate number 3, and we repeat the same procedure. Clear? So, this is how we can apply unit load method to get the details of this particular structure. Clear? And further, to get the D matrix and F matrix, we make use of this basic equation to find the elements in D matrix. Now, in step number 3, with the help of flexibility matrix equation, that is D minus DL equals to F into P. So, here P is the unknown. You know, you can call this as equation number A. P is the unknown, and here we can find DL matrix and F matrix by using this particular table. Clear? So, now let us find the matrix one by one. To find DL matrix, that is displacement matrix because of the applied loading. Clear? We have the order of matrix as 2 cross 2. We get 2 displacement values here. One is D1L and another one is D2L. D1L is the displacement at coordinate number 1 because of the applied loading, and D2L is the displacement at coordinate number 2 because of the applied loading. And we all know the basic expression to find all these displacements. The basic expression is integration within the limits 0 to L m into m1 dx divided by EI. Here, since we need displacement at coordinate number 1, take m1, and if you want displacement matrix at coordinate number 2, again within the integral limits of 0 to L, write m into m2 into dx divided by EI. Clear? So, we have all the values now. I know m and m1, moment at m and moment at m1 of all the segments of the particular beam. So, just get the summation of all these values within the respective limits. Now I'll start from CE segment. See, in CE segment, m into m1, 0 into 0 gives me 0, minus 40x into 0 gives me 0. I'll get only the moments because of these two segments. That means within the limits 0 to 2, I have the value of m as 40 into x plus 2 into the respective m1 value is x divided by EI. Look at the value of EI. So for this particular segment BD, the variation of EI is 2, that is given in the question. Therefore, it is 2 EI. This is for BD. Clear? Like that, you have to write the expression for all the segments individually for CE, EB, BD and DA. Since for CE and EB we are getting 0 values, I am not writing that particular expression. For BD, m into m1, and for DA, the value of m is again within the limits 0 to 2. Look at the respective limits, it is 0 to 2. M is 120x minus 160 into m1 value is x plus 2 into dx divided by, again look at the EI value, it is 2 EI. Clear? And if you solve this particular expression, we can get the final answer for D1L. And you can solve this particular expression manually or with the help of calculator. The final value for D1L will be minus 1013.33 divided by EI. Clear? Likewise, let us check the value for D2L. Again, D2L is m into m2. This is m and you have to multiply it with m2. 0 into x, 0. And I get expression for remaining 3 segments. Minus 40x into x plus 2, minus 40 into x plus 2 into x plus 4, minus 120x minus 160 into x plus 6 within the limits for individual segments. Let us write the expression here. For span EB, I'll get within the limits 0 to 2, it is minus 40x into x plus 2 divided by EI. For span EB, the variation of EI is 1. Then for segment DB, it is 0 to 2 minus 40 into x plus 2 into x plus 4 divided by 2 EI because the variation is 2. Next, the last segment, again there also the limits are 0 to 2 and it is minus 120x minus 160 into x plus 6 into dx divided by 2 EI. And if you solve this particular expression, we get the final value for D2L. So the final value will be minus 2880 divided by EI. Clear? So like this, we can get the DL matrix by using unit load approach. To get the elements in the F matrix, we use the same method. Clear? So I need this table to find F matrix also. Let us write the F matrix. So you all know F matrix is always a square matrix, and here the size of F matrix is 2 cross 2 and the elements inside the F matrix are F11, F21 and F12 and F22. And always remember, these two elements are symmetrical and this is the principal diagonal. Now let us find these elements one by one. So in step 3 itself, to get F11, I will use the expression within the integral limit 0 to L m1 into m1 into dx divided by ei. Clear? What do you mean by F11? F11 is the displacement at coordinate number 1 due to unit load applied at coordinate number 1. Clear? Therefore, M1 gives me the details of bending moment at individual segments because of the unit load applied at coordinate number 1. Therefore, whenever you want to find F11, you need to use this particular expression, M1 into M1. Likewise, if you want to find F12, since F12 and F21 are symmetrical, so I can write F12 equals to F21. So within the integral limits 0 to L, I have M1 into M2 into dx divided by ei. And in the same manner, if I want F22 within the integral limits 0 to L, should use the expression M2 into M2 into dx divided by ei. So now as usual, just like while finding DL matrix, clear? So we have taken the integration of m into m2, m into m1 of all the segments. So now to get all these values, again we need to take the details of m1, m2 within the integral limits of all these segments, and we need to sum it up. Again we are repeating the same procedure whatever we did in DL matrix. There we have taken moment details because of applied load also, and while finding F matrix we nowhere use the details of M, that is moment due to applied loadings. We take only the details about moment because of unit loads at different coordinates, at coordinate number 1 and at coordinate number 2. That's all. So now M1 into M1, see, for first segment 0, 0. We get details only because of these two segments. If you want, you can write the first segment is 0, the second segment is 0, and the third segment, that is BD, the limits are 0 to 2, and it is x into x, you can write it as x square into dx divided by 2ei, plus the last segment 0 to 2, x plus 2 into x plus 2, you can write it as x plus 2 whole square dx divided by, that is also 2ei. And if you solve this expression, you get the value for F11. It's very simple. Likewise, M1 into M2, 0, 0, it is x into x plus 4, x plus 2 into x plus 6, 0, 0 within the limits. Third span, it is x into x plus 4 into dx divided by 2ei. See, I am writing 2ei because there is a variation of 2 in this particular segment. Clear? That is not in formula. 0 to 2, the last segment is x plus 2 into x plus 6 into dx divided by, again there is a variation of I, that is 2. Now M2, x square, x plus 2 whole square, x plus 4 whole square and x plus 6 whole square. M2 into M2. Clear? That is rotation at 2, that is displacement at 2 because of the unit load applied at 2. So it is 0 to 2 x square into dx divided by ei plus 0 to 2 x plus 2 whole square into dx divided by ei. For the third segment, 0 to 2 x plus 4 whole square into dx divided by 2ei plus 0 to 2 x plus 6 whole square into dx divided by 2ei. So if we solve this, we will get the answer for F22. For F11, it is 10.667 divided by ei, and for F12 and F21, it is 26.67 divided by ei. and for the last value, that is F22, it is 96 divided by EI. So like this we can get the elements in F matrix. Clear? So till this point I need this particular table. So by using unit load approach we can find the DL matrix and F matrix with the help of this particular table. So now after finding F matrix, by using F matrix relation, that is D minus DL equals to F into P, we can find the unknown values, that is we can find the P matrix. Now in step 3 itself, by using the flexibility relation, that is D minus DL equals to F into P, we should find the P at the last. Clear? So I have got the values for DL and the values for F. I need to find this D. So here, since they have given support settlements, I should consider this D matrix. In previous 2 problems, we were not considering this D matrix because in those 2 problems, the supports are free from settlements. Clear? But here, support B and support C are getting settled by 10 mm and 5 mm. So how to calculate this D? Let us see now. So here D1 is at coordinate number 1. At coordinate number 1 we have B. Therefore that gives me the details about delta B, that is settlement at support B. And D2 is delta C at coordinate number 2. So B is settling by 10 mm and C gets settled by 5 mm. Just convert this to meters. Minus 10 divided by 1000, that gives me minus 0.01 meters, and this is minus 5 divided by 1000, so this gives me minus 0.005 meters. So I have used minus sign because if you observe figure C, I have marked the coordinate directions along upwards. That means upward forces are positive. That's why here settlement of supports is towards downward. That's why I have taken the negative sign. So I've got the values for D1 and D2. Just fill up the details in this particular equation. So D1, again D is a column matrix 0.01 and D2 is minus 0.005. Minus, you know the values of DL. D1L is minus 1013.33 divided by EI, and they have given the value of EI. Just convert into kilonewton and distance to meter square. If you do the conversion, the value of EI will be 18,000 kilonewton meter square. Therefore here it is minus 1013.33 divided by EI. At the position of EI, just write this value. And D2L, the value is minus 2880 divided by EI, write the value as 18,000. That equals to the F matrix. So just now we have got the values of F matrix. You just write the values along with the EI. So it is 10.667 divided by EI, then 26.67 divided by EI, and 96 divided by EI. So multiplied by the P matrix, that is P1 and P2. So P1 is nothing but RB and P2 is nothing but RC. So this is the required expression, and if you solve this particular expression, we can get the values for P1 and P2. So if you simplify this expression, so P1 and P2 will be, so this will be the inverse. This comes to this side, D minus DL divided by this F matrix. So I can write the F matrix in the inverse form, that is 10.667 divided by 18,000 26.67 divided by 18,000 and 26.67 divided by 18,000 here again, and it is 96 divided by 18,000. So it is inverse into d minus dl. So if you simplify this particular expression, you get 0.0463 and 0.155. Clear? And if you simplify this particular expression, you are going to get the values of P1 and P2 as, this is RB, this is RC, this will be equals to 17.893, 24.092, and both the values in kilo Newton. So this is the required value. So here, after getting the values of P1 and P2, that is the reactions, P1 refers for RB and P2 refers for RC. These two are the redundants we have assumed initially. So after getting these two values as plus 17.893 kilonewton and RC, it is plus 24.092. In previous step, I have written it as minus. Please make it as plus 24.092 kilonewton. So we need to mark these reactions on this beam. The value of RB is taken as 17.893 kilonewton and RC is taken as 24.093 kilonewton. So here our aim is to find the final end moments, that is moment at A, moment at B and moment at C. Since at C we have simply supported beam, the moment about C is equals to 0. But for sure we are going to get some amount of moment at support B and at support A. And also at support A we need to find the reaction RA. And all these quantities, that is MAB, MBA, MBC, can be found out by using equations of statics. Now, to find all these quantities, we need to consider the free body diagram of individual span, that is span BC and span AB, and we need to find these entities. And we require all these entities to draw the shear force diagram, bending moment diagram and elastic curve. Let us get these quantities one by one. So first I am going to consider span BC. So if you take the free body diagram of span BC, it is like this. So I have point load of 40 kilonewton, which is spaced at equal distance from both support B and C. And at C the bending moment is 0, and at B I don't know the value of bending moment, therefore I write the moment in positive sense. Since this bending moment is unknown, I should write this in positive sense. See, in first two problems we have assumed moments as redundants, therefore at this particular step we will get the final answer in the moment itself. Clear? So at this particular step we are going to get the final answer in the form of moment itself. But here in this particular problem, since we have sinking supports, we need to assume the reactions as redundants. If you assume the reactions as redundants, we get the unknowns in the form of reactions itself. Therefore we need to find the moments by using the conditions of equilibrium. So now call this point as P. I know the value of RB, but B has been shared for both the span BC and BA. Therefore, this will become RBC and this is end support RC, and the value of RC is 24.093 kilonewton. Clear? So now to find RBC, you can use the equation summation of Fy equals to 0 upward forces as positive. See, RBC is acting in upward and RC is acting in upward and minus 40 is acting in downward direction. I know the value of RC, substitute here, and if you solve this particular equation, you are going to get 40 minus 24.093, you'll get RBC value as plus 15.908 kilonewton. Clear? So we got the RBC value as plus 15.908 kilonewton. Now we should find this MBC. To get the value of MBC, take moment about B. If you take moment about B, and I'll consider clockwise moments as positive, so we are going to get 40 into 2, then this MBC is acting in positive direction, therefore plus MBC, then minus RC into 4. You know the value of RC, minus RC into 4, and this is 0. Substitute the respective value for RC, and if you solve this equation, we are going to get the value for MBC as, it is plus 16.37 kilonewton meters. If you get the positive value for MBC, whatever the direction you have assumed is correct, and the same value can be marked here. Clear? MBC, it is plus 16 point clockwise 37 kilonewton meters. Clear? Now you can consider the span AB, and if you write the free body diagram of span AB, this is A, this is B, and again at the center of the span we have point load of 80 kilonewton, and this is 2 meters, and you can call this point as Q, and here we can call this as RBA and this as RA. Clear? And we have some moments here, and here if you look, we know the value of RB, the reaction, it is 17.893. So RB is share between RBA and RBC. Clear? So the value of RB is known. How much? 17.893. And just now in the previous span we got the value for RBC. And the value of RBC is plus 15.908. The only unknown here is RBA. So if you solve this particular equation, you can get the value of RBA. And the value of RBA is 1.985 kilonewtons. 1.985 kilonewton. Clear? So now, once you got the RBA, just by using the force equilibrium condition, summation of Fy equals to 0, upward forces as positive. Clear? So I have RA is acting in upward direction, RBA is acting in upward direction, and minus 80 because it is acting in downward direction. You know the value for RBA as 1.985, substitute here, and if you solve this particular equation, you can get the value of RA as 78.015 kilonewton. Clear? So now we should find the moments at A and at B. So if you consider the joint equilibrium condition, that is MB is nothing but it's a combination of MBA plus MBC, and at intermediate support the summation of these moments should be equals to 0. This is called joint equilibrium condition, and in previous step we have got the value for MBC, therefore MBA plus 16.37 equals to 0. Therefore, MBA should be equals to minus 16.37 kilonewton meters. Like this, we can get the value for MBA. Since it is minus, it is acting in anti-clockwise direction. 16.37 kilonewton meters. Clear? Minus anti-clockwise direction. The same can be written here also. Here both the moments are equal and opposite. One is clockwise and another one is anti-clockwise. Now, I don't know the value for MAB, just mark it in positive sense, MAB in clockwise direction. Now take moment about A, that is summation of MA equals to 0, clockwise moment as positive. Just I am repeating the steps. Once you learn for span B, the same steps can be repeated for span AB also. That is applying the equations, conditions of equilibrium. So now if you take moment about A, it is plus 80 into 2, then minus 16.37, which is acting in anti-clockwise direction, then minus RBA into 4, then plus MAB equals to 0. If you solve this particular equation, you are going to get the value for MAB as minus 135.69 kilonewton meters. Clear? So now here I have got the value of MAB in negative sense. Therefore, whatever the direction I have assumed is wrong. So while marking this moment on the main beam, you should mark in anti-clockwise direction like this. It is 135.69 kilonewton meters. Since I have got the negative value, you have to mark it in anti-clockwise direction. Clear? So this is how we should find the final end moments in case of beams which is having sinking supports. After this, if you want to draw the shear force and bending moment diagram, we can repeat the same procedure that we have did in previous two problems. Now to draw the shear force and bending moment diagram, I should write the reference lines at the point indicated at A, at B, at C, and also under the point loads, and I have given the names, this as P and this as Q, and we should find the bending moments at these 2 points also. Just write the reference lines. This is a datum. So now you know the value of RA. The value of RA is 78.015, which is positive. So just move, start from 0, just move upwards up to a point 78.015 kilonewton, and it is constant till point Q. Here I have plus 78.015 minus 80, that gives me minus 1.985. So here I have minus 1.985 kilonewton. So this is constant till point B. So here also I will be having minus 1.985, and here the reaction RB is moving in upward direction, therefore minus 1.985 plus 17.893 gives me plus 15.908 kilonewton, and this is constant till point Q, constant till point P. Here I have plus 15.908 minus 40, that gives me minus 24.093 kilonewton, and it is constant till point C. Here I have minus 24.093, and at C I have plus 24.093. Minus and plus of same magnitude leads to 0. So below the datum line it is negative, above the datum line it is positive, and this gives me the shear force diagram for the given beam. This you have learnt in 3rd semester in strength of materials. Clear? So now after sketching the SFD, you can write the reference line to sketch BMD. See, I have end moments here. I need to find the span moments at point Q and at point P. So here in the free body diagram itself, either to right side or left side, consider the section and find the bending moment. I consider section to the right side because it is very simple to find the bending moment value. So if I consider the section to right side, I have only one force, that is RC. RC into 2 gets me the bending moment at point P. It is 24.093 into 2. Upward moments are positive here. Therefore, this gives me 48.19 kilonewton meters. This is the moment at point P. Now, in the same manner, you can find the moment at point Q. Again, you can consider section to the right hand side or to the left hand side. I'll take to the right hand side again. So it is RBA. The value of RBA, you know, it is 1.895 into 2. Then this is also acting in upward direction. Therefore, 16.37 in positive sense gives me the value. This gives me the value of 20.34 kilonewton meters. Clear? Like this we can find the span moments. Now you can mark these moment values on the beam. You all know if the arrow mark is downward, you can mark the moments in the downward zone. If it is upward, you can mark the moments in upward zone. First we mark the end moments. At C it is 0. At A I have 135.69 kilonewton meters. At B I have 16.37 kilonewton meters. And at P I have 48.19 kilonewton meters. And at Q I have, just now we have calculated, it is 20.34 kilonewton meters. So like this you can mark the bending moment values, both span moment and end moments, and you can join all these points according to the nature of loading. I have point loads. You know how to join the values because of the point loads in a linear manner. As usual, above the reference line it is positive, below the reference line it is negative. This is how you can sketch the BMD for the given beam. Clear? So now we need to sketch the elastic curve. So you all know from with the help of bending moment diagram we can sketch the elastic curve. So have one point of contraflexure. You know what is point of contraflexure? This is a point where bending moment is 0 and also it shifts its sign from positive to negative or negative to positive. With the help of this bending moment diagram, we can sketch the elastic curve. So here, since the supports are at different levels, at B we have 10 mm settlement and at C we have 5 mm settlement. You can indicate the points like this. Now you can approximately figure out this point of contraflexure. So here from A to this particular point up to point of contraflexure, we have negative bending moment. Therefore there you should show the hogging nature of curve, and from this point of contraflexure to till point C, bending moment values are in positive. Therefore there you can show the sagging nature of curve. Here both the supports B and C are at different levels. So B has been settled by 10 mm and C has been settled by 5 mm. You can show that here. Then wherever you have negative bending moment, at that position the curve will be in hogging nature, and in the positive bending moment zone the curve will sag. With the help of bending moment diagram, approximately you can figure out the point of contraflexure. You need not to find the position of contraflexure here. So now with the help of this POC, you can just show the hogging and sagging nature of curve. Since A is fixed, here you won't get any kind of deflection. Clear? So this is our elastic curve. From here to here you can show this is delta B. From here to here it is delta C. Clear? See, somewhere between A to this 80 kilonewton load, we may get this point of contraflexure. So here the curve is in hogging nature. Then up to this point we have positive bending moment, therefore the curve is sagging in nature. So this completes the analysis of this particular beam subjected to sinking supports. In next session I am going to take up the portal frames which may subjected to sway and no sway. Thank you.